In this video, we're going to be learning about limited exponential growth and how to understand it mathematically by using the logistics equation. In order to do this, we don't actually need to learn any new concepts like we did for arc length or partial fractions. We're just dealing with differential equations. We need to apply the knowledge that we already have to describe a situation where you have exponential growth, but where that growth will taper off at some limiting value. Imagine that we have a population of bacteria. Let's say each bacterium can produce 2 offspring over some period of time. Now what we have is a system that will multiply itself by 2 at every step, an exponential system. But what if we only have enough food to feed 1 million bacteria? In that case, as the bacteria population approaches 1 million, its growth will slow down and never cross over the million mark because it will be harder and harder to feed all of the bacteria. Our graph will need to look something like this, with the y-axis representing the population of bacteria and the x-axis the amount of time passed. The bacteria population will start near 0, increase exponentially, and then somewhere in the middle begin to slow down until it's so close to the upper limit that it's basically not growing anymore. Now the graph I've shown here can represent many things. It could be the bacteria population, it could be the human population, it could describe economic growth. We can describe all these different things with the differential equation dy over dx equals ky times the quantity 1 minus y over a, where a and k are arbitrary constants. So how does this equation work exactly? Well, to understand that, we can use Euler's method to approximate it. I'm going to use Excel for this purpose so I can create automatic calculations. I'll establish a column for x values and then a column for y values. We'll start at x at 0 and we'll start with y at 1. Now we need a formula, so I'll go ahead and choose one at random. Let's say one where k is equal to 1 and a is equal to 100. Now let's make dx equal to 1, so this is as simple as possible. I'll program each cell in the x column to increase by 1. Now for y values, we have to put in our dy dx based on the values of the previous x and y values, and then multiply it by dx and add the previous value. Now I can copy that down to subsequent cells, and there we have it. Now as you can see early on, this function looks nearly exponential. If we round it up generously, we could go from 1 to 2 to 4 to 8 to 16. That looks pretty familiar. But the farther up we go, that progress slows down, and finally it rounds up to 100 and stays there. So there's how differential equations work. The AP test will likely ask you to analyze various parts of differential logistics equations. Let's try one example without help from the computer. So for example, if we had a differential equation that was supposed to chart deer growth over time, let's say dr over dt equals 2r times the quantity 1 minus 200 over r. What is the limit of this population of deer? 200. Because if r is equal to 200, you see that in the equation you'll get 1 minus 200 over 200, which is 0. So there will be no change at that point. So, what is the general equation to our differential equation? The equation that can tell us the exact population at a point, not just the change in population. That is, using the same constants as our differential equation, and of course the unknown constant c, a over 1 plus e to the power of negative kt over c. Finding the solution is fairly tricky. You'll just need to memorize it, really. If you'd like to see how to actually solve the differential equation, go and click on this annotation or find the link in the video description. I highly recommend you do this, as it will make memorizing the equation a lot easier. So we can analyze a few features of this equation to get an idea about why it works for the idea of limited growth. Let's take the limit where t approaches positive infinity. That means that the exponent of e becomes a huge negative number, approaching 0. So we just have a over 1. Therefore, we know that the equation approaches the limit of growth, a, as it goes off towards infinity. Going towards negative infinity, we get a huge exponent in e, so we have a over a value approaching infinity. Therefore, it approaches 0, the bottom of our logistical growth. So now let's do a practice problem where we have to take a differential equation. Let's just use the one we had earlier for deer population growth and find its solution using the equation I'm sure you've already memorized since I just showed you, and then solve for the constant c by using an ordered pair. So first let's define our ordered pair. I'll just say that when t equals 0, r is equal to 5, or you could write it as 0 and 5 in an ordered pair. So back to our first step, we need to identify our two constants. So let's look at our general equation for logistical growth. Ky times the quantity 1 minus y over a. And so we have to find a and k here. And so we can see that k is equal to 2 and a is equal to 200. Okay, so now we know that. Let's take the formula we memorized. So we have a over 1 plus e to the negative kt over c. So now we just have to substitute in a and k and rewrite the values that we already know. Great, we are really close. And so now, we need to find the value of the constant c. And we can solve this like a simple algebra problem if we just put the values of r and t that we already established. And so if there's like a question like this in the AP test, it'll give you a ordered pair like that, and you'll have to solve for the equation that'll get you the logistical growth. And so let's put in those values. E is to the 0th power, so we just have 1, and so we multiply both sides by 1 plus 1 over c, and then divide by 5 on both sides, and then 200 over 5 gets us 40. And then we subtract 1, we divide out, and then multiply by c, and then we get c is equal to 1 over 39. And so now we can just go back to our original equation, and we have 1 over 39, but that's in the denominator, so we can just flip the 39 up, and we get 200 over 1 plus e to the negative t times 39. Our next video is going to be on partial fraction decomposition. For that, please click on the annotation on the right. And I'm also going to be delving deeper into the ideas of logistical growth. Click on the annotation on the left.